in the previous section where we were finding zeros of polynomials. Just in this particular section, we're going to add in some thoughts about what happens when you have complex zeros. So, pardon me. It turns out that, in this first part, if you have a polynomial that has all real coefficients, so meaning the coefficients don't have any i's in them at all, and you know that a plus I is a zero, then we also know that a minus bi is also a zero. For example, remember when we talked about, we introduced the number I through solving the equation x squared plus 1 equals 0. Where we got that square root of -1. If you think about solving that equation, you'd have to move the 1 to the other side, so you get x squared equals -1. When you take the square root of both sides, you get plus or minus I, right? You get the plus I and minus I. Remember, complex conjugates are when you switch the sign in the middle, right? If it's a plus, you switch it to a minus and vice versa. That's all this theorem is saying, is that if you know that a plus bi is a zero, then we also have to have that a minus bi is a zero. So let's use this in a couple of examples and then use this idea to help us find all of the zeros of a polynomial, but we've got some extra complex ones involved. So we've done problems like this before, where we've asked to construct a polynomial that has certain roots. When we have a zero or a root, either or, those two words mean the same thing. If we have that the number a is a root, is a zero, what has to be a factor? So if they have 3 is a zero, what has to be a factor? The, not quite -3, but the factor has to have an x in it. What was a linear factor? If 3 is a zero, then something is a factor. Ooh, that's not good for Friday. That's going to be on there. If something is a zero, then what has to be a factor? It's in that list of things that we had in that first section we talked about. Let's think about it this way. If you started with, if you had ended up with x equals 3 and something was a zero, what's on the other side? Going backwards from here. What would be on the other side of the equation if I go from here up? How do I get 0 on this side? Ah, so if 3 is a 0, what has to be a factor? X minus 3, right? It's x minus the number has to be the factor, right? Don't forget that, because we're already talking about doing factoring, right? That's the whole point of this section is doing the factoring. Okay. If something is 0, 0, then x minus that number is a factor. So looking at this, it tells you that -1's a 0. So what has to be a factor of the polynomial? X plus 1, good. If 1 plus I is a factor, what has to be a 0? It'd be x minus the whole 0, right? Same rule applies for complex zeros. If something is a 0, then x minus that thing is a factor. So what would be the third factor here? Yeah, so there's a third one, exactly. So again, the rule is that if something's a 0, x minus that something is a factor. Okay. Now, this is another type of problem that we've talked about before. What would be the degree of this thing if we multiplied it out? Cubed, right? We've got 3 factors here. You have an x times an x times an x will give you an x cubed. So this does give you a third degree polynomial. The last part, though, is what do we need to do with this to make sure the end behavior is correct? Since, and this is a good review for the exam, since the degree is 3, do both tails point the same direction or opposite directions? Opposite. So if it's positive, you go from what to what? It was a positive at leading coefficient. Lower left to upper right. Is that what this is asking for? Is that upper left to lower right? Because this says as you go to the right, we go which way, up or down? Down. So that's not upper left to lower right, right? Or sorry, lower right, left to upper right, right? It's the other way around. How do we make it go the other way around? Well, we need to put in front a negative. Good. Yeah, we need to put a negative in front of this. Okay. So this negative here is to handle the end behavior. So again, creating these polynomials, you have something as a zero, x minus that something has to be a factor. We've played around with making sure we have the right y-intercept. This is just playing around making sure we have the correct end behavior. I'm not going to bother multiplying that out. The reason why you want the complex conjugates is if you multiply these out, anything that has an I in it is going to cancel when you have those complex conjugates. All right, let's look at the next one. What's that?
Sorry if you already answered.
Oh, I'm sorry, I didn't see your hand.
No, it's okay.
Just holler at me or throw something at me. Yes, yeah.
So why would it not be like? Why would the signs not flip for? Oh wait. Yeah. Why would the signs not flip at the 1 plus I? Like, you know how you flip the sign for x plus 1? Why would it be x plus? Is it because the whole thing is the
So we're doing this one, I can actually think of as x minus a negative 1. That's why I've got the parentheses around the other ones. Is that what you're asking me?
Yeah.
So you could write it as flip it. You want to flip all the signs. Is that what you're asking me?
Yeah.
Yeah, you can absolutely do it that way.
Okay.
I just got parentheses around it. Notice if you distribute that minus sign, you'll get x minus 1 and minus I. That would correspond to the first one. And the other one would be a minus 1 and a plus I for the second one. It would just be distributed that minus sign through the parentheses. I just put parentheses around it.
Okay.
You can absolutely flip all the signs if you want. Sorry, is that what you were asking?
Yeah, that's what I was asking.
Yeah. Sorry, it took me a second to get to the uptake on that one. Other questions on that? Sorry. Like I said, if I don't see your hand, just throw something at me. I said that to a student once, and they actually did. Water bottle came whacked up against the empty water bottle whacked up against the board. It's kind of funny. All right. Anyway, let's look at the next one. You want to find a polynomial with real coefficients with the smallest degree possible that has those two things as a root. So this is just illustrating that theorem we talked about at the beginning. If we know that 6 minus 2i is a root, is a 0, what else has to be a 0? Good, 6 plus 2i. If we know that negative 3 plus I is a 0, what else has to be a 0? Negative 3 minus 2i. So the zeros have to be 6 minus 2i, 6 plus 2i, because they have to occur in conjugate pairs. And negative 3 plus I and negative 3 minus I. So what would your polynomial look like then? Do it just like we did the previous one. Yep. Yep. And then the same thing for the other two. Okay. So again, the whole point of this particular example is that, again, your roots occur in conjugate pairs. So if your 6 minus 2i is a 0, your 6 plus 2i also has to be a 0. Negative 3 plus I has to be a 0. Negative 3 minus 3i has to be a 0 as well. Again, if you were to multiply all of this out, anything with an I in it will cancel out. I'm not going to expect you to multiply that out. Is okay? Yes. Oh, yeah. If you're coming late and you want to ask us, you know, appreciate it. All right. So let's go on to more problems like we were doing last time. But before we get there, when we add in complex numbers, we can start talking about how many roots a polynomial of a certain degree must have, or how many zeros it must have. So turns out that we have a result that's referred to as a fundamental theorem of algebra. It has the words fundamental theorem in it, probably fairly important. So if we have a polynomial of degree n, and it has complex coefficients, we'll only deal with anything that has real coefficients. But the theorem is that if it has complex coefficients, then f has exactly n zeros when we count multiplicities. So what that means is that if you have a degree 4 polynomial, it has 4 roots, 4 zeros. If you have a degree 7 polynomial, it has 7 zeros. You have to count multiplicities. Remember what's multiplicity again? What tells you multiplicity?
All the degree.
The degree on that factor, right? The degree on the factor tells you the multiplicity. Okay. Counting multiplicities, you get exactly that many zeros. So that's what the fundamental theorem of algebra says. So looking at this first example we have on the page, what's the degree of that polynomial? 4. So how many zeros are we going to be looking for? 4. Good. All right, so the first thing, notice they already told you a 0, right? They told you that negative 6i is a 0. Since negative 6i is a 0, what else has to be a 0? 6i, right? So when we're going to do this one and find all of the zeros, we're going to use our synthetic division idea again. Still, it works with complex numbers just as well as it works with real numbers. So let's use synthetic division. So put our coefficients across the top. We'll put negative 6i up in the corner. What do we do first with synthetic division? Yeah, drop the number down, and then we multiply, and then add. Good. Notice that these are not like terms, right? So the best we can do is just bring down negative 6 minus 6i. Right? Best we can do. They don't combine. Now we're going to multiply the negative 6i times the negative 6 minus 6i, right? Negative 6i times the negative 6 will give you a plus 36i. Negative 6i times negative 6i gives you 36i squared, and I squared is negative 1. So that becomes negative 36. We add down and get what? Yeah, the 5 plus 36i. Good. Multiply again. Negative 6i times 5 will give you negative 30i. Negative 6i times 36i. 6 times 36 is 216. So you get negative 216i squared. But I squared is the same thing as negative 1. So we get a positive 216. That's a good sign. When we add down, negative 30i. You're told that negative 6i is a 0. So what should this turn out to be to make sure we get 0 at the end? We should get 0 at the end. So this number here should be Negative 180, because when we add down, we should get 0. So let's see, make sure we really do get negative 180. Negative 6 times negative 30 is positive 180. I times I is I squared, which is negative 1. So we do get negative 180. Add down, we get 0. Okay. We better have gotten 0 because we were told that it's a 0, right? You're told that it's a 0, so you better get 0. All right, so that's step 1. We started with degree 4, so these coefficients would be for a degree 3. Remember, our goal is always to get down to degree 2, and we can use quadratic formula if we need to, right? What's the other 0 we can use now? 6i. Do the exact same thing. This one is the first step when you have a complex 0 is usually pretty well. It's a little bit more difficult than the second, and you'll see what I mean. Bring down the 1. 1 times 6i is 6i. What happens now when you add? Yeah, the i's cancel. You just get a negative 6, right? Negative 6 times 6i is negative 36i. What happens again? They cancel out. We get a 5. 6i times 5 is 30i, and that gives us 0. This should always happen. If you have a complex 0 and run it through your synthetic division, and then do the conjugate and run it through your synthetic division, you should not have any i's here. They should all cancel out in that second step. If they don't, you've done something incorrectly somewhere along the line, usually an arithmetic error. Okay? Once you go through it twice, the i's should disappear. Okay. We started with degree 4, now we're at degree 2, right? We've gotten to the point where we have f of x is x plus 6i times x minus 6i times x squared minus 6x plus 5, right? That's how that would factor so far. X minus 0, right? The x minus the 0. X minus a minus 6i, x minus 6i, and then these are the coefficients that are left. You see how this factors? Five and 1 work, right? So what are your zeros then? Well, so the zeros are negative 6i, 6i, and the other two are 5 and 1. Oops. So this is finding the zeros. This is writing f of x as linear factors, a product of linear factors. That's okay? All right, let's do the next one. This one will be a little bit more arithmetic involved, if you will, but still the same concept. We have a degree 4 polynomial. They tell you that 1 plus 2i is a 0. What else has to be a 0 then? 1 minus 2i. So right away, this tells you basically the first two steps, right? You've got 2 zeros to work with, so do the synthetic division twice to start with, okay? So again, we'll put 1 plus 2i up in the corner. Leave yourself some space as you go across because you're going to have the complex numbers to write in. Oops. So the coefficients we have are 1, negative 4, negative 6, 20, and negative 75. First step, we bring down the 1. Next thing we do is multiply. And then what do we do? Add down. What do we get? Negative 3 plus 2i, right? Now we're going to need to do a little bit of arithmetic. So you might want to work off to the side to do your arithmetic because I have to distribute everything, right? I have to multiply. I'm using FOIL, right? Got to do all my distributive stuff. So if you need to work off to the side, please do to do your multiplication. But notice that I'll have 1 times negative 3, which gives me a minus 3. 2i times 2i will give me a 4i squared, which is minus 4. So I've got minus 3 minus 4, we'll get negative 7. And then we'll have plus 2i minus 6i when I do the outer and inner terms, if you think about FOIL, right? 1 times 2i is 2i. 2i times negative 3 is minus 6i. So we should get negative 4i. Again, if you need to write it out to the side, please do. I'd have 1 plus 2i times negative 3 plus 2i. So if you multiply it out, that's what it would look like, right? I just simplified it along the way. Please write it out if you need to. Next step is to add down negative 13 minus 4i. So far, so good? Do it again. 1 times negative 13 is negative 13. 2i times negative 4i is negative 8i squared, which would be plus 8. Negative 13 plus 8 is negative 5. 1 times negative 4i is a minus 4i. 2i times 13 is negative 26i. Negative 4 minus 26 is negative 30i. And then add down. Again, if you need to write it off to the side to do the arithmetic, please do. Okay. Just like I did over here, right? Just literally write down 1 plus 2i times negative 13 minus 4i and do the distribution. Yes.
Wouldn't that be 15 minus 35? Because it's 20 plus negative 5.
What did I do? I'm sorry.
Yeah, the most recent.
Oh, yes. I did. That's a positive. Thank you. Thank you. That would matter here in a second. Thank you very much. All right. What answer do you need to come up with here at the end? What should this turn out to be right here? Positive 75, right? We need to end with 0. If it's not positive 75, you've made an arithmetic error somewhere. Okay? Has to be positive 75 at this point. 1 times 15 is 15. 2 times negative 30 is negative 60, and then we'd have an I squared. 15 plus 60 does give me 75. 2i times 15 is positive 30i. 1 times negative 30i is minus 30i. Those do cancel. I really do get negative 70 or positive 75. So we get 0. There's a little bit of arithmetic involved in those, right? Again, if you need to write it off to the side, please do. Apparently, I should have of course, I just couldn't add 20 and negative 5 together. That's my issue. All right. Again, we started with what degree? 4th. So right now we're at degree 3, right? So how do we get to the next one? What else has to be a 0? 1 minus 2i. Good. Same process. Bring down the 1. Now again, we said that at this next stage, what has to happen? The i's are going to cancel, right? So when I do this multiplication, I have a plus 2i up here. I better get a minus 2i here, right? We've got a minus 4i here. We better get a plus 4i here, right? So you know what the answers have to be as you're going along, or at least part of the answers as you go along. So it helps you keep track of if you're going to make a mistake or not, right? 1 times 1 minus 2i is 1 minus 2i. Add down, we get negative 2. That makes the multiplication a little bit easier. Negative 2 times 1 is negative 2. Negative 2i times 2i is plus 4i. And again, they have opposite signs, like they should. Add down, we get negative 15. And then we better get negative 15 plus 30i, which we do. Right? That makes that a 0. So far, what does your factorization look like? Very good, right? So we found that these two things are zeros, so we know that x minus those numbers are factors, correct? Those are factor theorem we talked about before. If you have a zero, then x minus that number is a factor. So I have those two linear factors, and then this third one, right? Does that third one there, that quadratic piece factor? Yes. Good. So this again factors f of x into linear factors. Linear factors because we have x to the first power in each of them. And then again, we can get the zeros. What are the zeros? Well, the first two are 1 plus 2i and 1 minus 2i. What are the other two? 5 and negative 3. Good. What questions do you have? So far, so good? Let's skip the next one. I wanted to go on to the 5th degree polynomial. Make sure we have enough time for it here. So skip the next one. This one, we've got a 5th degree polynomial. They tell you that negative 2i is a 0. So what else has to be a 0? 2i. Now, if we run negative 2i through a synthetic division and 2i through a synthetic division, what power are we down to then? Third, right? Because we've only gone through it twice. We said our goal was always to get to quadratic, so that we always use quadratic formula, it works, right? So there must be a way to find another 0. Was that? Oh, you graph it. Yeah, we want to look for those rational zeros again, right? Like we did last time. So let's write those down first. When we look at possible rational zeros, what do we look at again? Good. So we need factors of 12 and factors of 2. Remember doing these last time? What are the factors of 12?
1, 2, 3, 4, 6, 12.
6 and 12. Good. Yeah, so again, they have to occur in pairs, right? So start with 1, go up, and then keep track of the other ones as you're coming down and meet in the middle. All right? 1 and 12, 2 and 6, 3 and 4, and there's nothing in between 3 and 4, right? We're done. Once you meet in the middle there, you're done. Okay. Factors of 2 is pretty easy. 1 and 2, good. Now again, for possible rational zeros, we need to make fractions, right? What goes on the top of the fractions? Yeah, the factors of 12, and the denominators are factors of 2, right? And again, we can always use plus or minus, right? Right. So what are your possibilities?
1, 2, 3, 4, 6, 12.
Okay.
1 half, 3 halves.
That's it. Good. So remember, these are all your possible numerators. These are all your possible denominators. So Jasmine just did 1, 2, 3, 4, 6, and 12 all over 1. And then 1, 2, 3, 4, 6, and 12 all over 2. But you've already taken care of 2 over 2. That's 1. 4 over 2 is 2. 6 over 2 is 3. 12 over 2 is 6. So you already had those listed. So you have to list them again. All right. So if we graph this, and again, on the exam, you won't have to take time to graph it. If I want you to do it, I'll have the graph on the paper for you. You just need to use the graph. Okay. So you don't have to worry about, you don't need to worry about having a graphing device if you don't have one. Okay. Do-do-do-do-do. Make sure I have the right function popped up here. So we had 2x to the 5th minus 5x to the 4th plus 4x cubed, not c, x cubed, minus 17x squared minus 16x plus 12. Which number might you want to use? I'd probably use the negative one. It's a little bit easier to multiply by, all right? What else might have worked? This one looks like a half. That one's definitely 3, right? You could use any of them. We only really need one of them, right? Okay. All right, so we'll use negative 1 when we get to it. Okay. All right. So we have now three of them to play with, right? So let's do the complex ones first. Let's do the 2i. You could use the negative 1 first, by the way, if you wanted to. What do we do first? Drop the 2, and then multiply. So we get negative 4i. Those are not like terms, so we just get negative 5 minus 4i at that next step. When you multiply, what do you get for the next one? Yeah, negative 8 plus 10i. So again, the negative 8 comes from negative 2i times negative 4i gives you positive 8i squared. I squared is negative 1, so it makes it negative 8. And then negative 5 times negative 2 is plus 10i. Add down, we get, good. Multiply. So negative 2i. Negative 2i times 10i is negative 20i squared. That's what makes it positive 20. Negative 2i times negative 4 gives you plus 8i. Add down, we get 3 plus 8i. What do we get next? Good. 16 minus, you're right, it is a minus. I wrote a plus. 16 minus 6i. Good. Negative 6i. Negative, it better be negative 12, right? Because we need to end at 0. Everybody okay with the arithmetic? Like I said, it's a little bit more complicated than the previous section, but same concept, right? Same exact concept that we were doing. We also know that 2i is a 0. Now again, since we're doing the complex number and its conjugate, at this step, what needs to happen? Yeah, the i's need to cancel, right? If you do the complex 0 and then do its conjugate and your i's don't cancel, you've made a mistake somewhere. Okay? There's an error somewhere along the way, right? Bring down your 2. When you multiply, you get 4i. Add, you get negative 5. I went away, right? Multiply, negative 10i. Add, negative 4. Multiply, add, good. Multiply, add, 0, which is what we should get, right? So far, so good? Started at 5 for the degree. This is degree 4. This is degree 3. We still need to get out to degree 2. That was why we used the graph, right? We said try negative 1. right? Try -1. Bring down 2, multiply, add, multiply, add, multiply, add 0. So we did get a 0, right? So far, what does the factorization of f of x look like? Good. Yeah? And that last piece is going to factor just from what we saw before. You said that it looked like, for example, you said that it looked like 3 was a root. 3 was a 0. If 3 is a 0, what's the factor? X minus 3, good, right? What's the other one have to be then? If I know that I have x minus 3, what does the other factor have to be? To get 2x squared, if this is x, this has to be 2x. And to get a plus 3 on the end, we have to have minus 1 to get that multiplication to work. What 0 does this correspond to? A half, which is what you said the other one was, right? So I don't even think about the factoring. Again, if you don't see how it factors right away, you can always use quadratic formula to find the other 0. Questions on that one? Let's do the last one. All right, so again, when they give you one complex 0, they really give you 2, all right? You're told that 1 minus I is a 0, so what else has to be a 0? 1 plus I has to be a 0, right? We have a degree 5. Using those 2 zeros can get us to degree 3. We still need one more 0, right? So that's why we're going to do the possible rational zeros again to start with. For your possible rational zeros, you need factors of the constant, which is 64, factors of the leading coefficient, which is 3, and then make all those fractions, right? Right? What are your factors of 64? 1 and 2, and 3 doesn't work, 4 does, and 8 does, right? Because 8 squared is 64. Now it's 16, 32, 64, right? Matching them up. Again, that's that meet in the middle approach, right? 1 goes into it 64 times, 2 goes into it 32 times, 3 doesn't, 4 goes into it 16 times, 5, 6, 7 doesn't, 8 squared gives you 64, so you met in the middle now. Factors of 3 are easy. 1 and 3. So what are your possible rational zeros?
1, 2, 4, 8, 16, 32, 1 third, 2 thirds, 4 thirds, 8 thirds, 16 thirds, 32 thirds, 64 thirds.
Yep. And then what can we do with all of those? Plus or minus. Good. So again, the factors of the constant are your possible numerators. The factors of your denominator are the factors of your leading coefficient are the possible denominators, all right? So we're just doing all of the factors of 64 over 1, all of the factors of 64 over 3. That's how we're getting the list. Does that make sense? Okay. Let's graph this and see if we can pick out 1. We just need 1, right? Don't need a bunch, we just need 1. Because we can already get down to cube by just using the complex. All right, so let's go over here. Get that one out of here. 3x to the 5th minus 4x to the 4th plus 50x cubed minus 60x squared plus 32x plus 64. It is off. Thank you. Appreciate that. All right. Notice that no matter how far I zoom out here, I only see the 1. All right. I only see the 1 time where it's crossing the x-axis. Let's see if I click on it. Looks like that's about negative 2/3, right? 0.6666 repeating is 2/3. Okay. So we probably want to use negative 2/3, just as a guess. Okay. All right, let's go back over. In this case, so I don't have to do so many complex number multiplications, let's use the negative 2/3 first. You can always do the rational 0 first if you want. The only reason why I'm doing the rational 0 here first is because I'm just trying to minimize the number of complex number multiplications I have to do. Okay. Bring down the 3. Multiply, you get negative 2. Add. Multiply. It's positive 4, right? Because it's going to get this. The 3 will go into the 6 2 times. 2 times 2 is 4, right? Add 54. I mean, you can always use your calculator if you need to. Multiply. Add. Good. Multiply. 64. Add gives you positive 96 this time. So when you multiply, I bet you get negative 64. It's the same multiplication, right? That, and we better get negative 64, so we get 0. Okay. So again, just the same thing we've been doing, right? And use your calculator on the arithmetic. You don't have to try to do it in your head. We'll all have calculators. All right, we found 1 0. What's another 0? 1 minus I. Bring down the 3, multiply. Good. Add down. Good. Now again, if you need to write off the arithmetic off to the side, you can. But I can do it here step by step. 1 times negative 3 is negative 3. Negative I times negative 3I is positive 3I squared, which is another negative 3, right? So we get negative 6. Then we get plus 3I and minus 3I. It looks like the i's go away there in the middle. Okay. So we just get negative 6. Add down, we get 48. Multiply 48 minus 48i. Add down, we'll get negative 48 minus 48i. What number better we get when we do this multiplication? We better get negative 96, right? We have to get 0 when we're done, correct? Okay. So let's see if we get negative 96. Man, I hope so. 1 times negative 48 is negative 48. Negative I times negative 48i is positive 48i squared, but that's negative 48. We really do get negative 96. Negative 48i plus 48i, they do cancel, so we really do get 0. Again, we started off with a 5th degree. So what are we at now? 3rd degree, right? We need one more. What's the other 0? 1 plus I. Good. Three multiply, we get was plus 3i. When we add down, we get 0, right? That all completely went away, didn't it? Multiply, 0, add, 48, multiply, good, add, 0, which is good, right? We better get 0, correct? So again, at this point, what does the factorization look like? X plus 2/3, good. Good, yep. Good. And then the last one's going to be good. All right. So again, we found 3 zeros. X minus those numbers are factors. We started with 5th degree. We did it 3 times, so we're down at 2nd degree. That last part is 3x squared plus 48, because those are the coefficients for the quadratic. Unfortunately, that doesn't factor, right? Because it's got a plus in the middle instead of a minus. Or minus you could factor as a difference of squares. So again, let's just set that piece equal to 0. You could use quadratic formula, but that's overkill here. Let's subtract your 48 and divide by 3. If you subtract 48 and divide by 3, you should get negative 16. So what happens when you take the square root of both sides? So you get plus or minus square root of negative 16. So we get plus or minus 4i. Good, yeah. The square root of the negative gives you the I. Square root of 16 is 4. And remember, anytime you do square root of both sides of an equation, you get plus or minus. The only tricky part on this one, since we ended up dividing out the 3, I have to be a little bit careful when I write the factoring. There's going to be one more thing we have to write in here. But notice again, 4i is a root, 4i is a 0, so x minus 4i is a factor. Negative 4i is a root, so x plus 4i is a factor. Unfortunately, what would the leading coefficient be of this polynomial, the way we have it factored, if I multiply everything out? What would the leading coefficient be? I'd have an x times an x times an x times an x times an x is just x to the 5th being 1, right? What's the leading coefficient supposed to be? What did it start out being? 3. Do you see a common factor here in those two numbers? Yeah, there would be a 3 out in front. We divided out that 3 right here when we solved, right? So there'd be a 3 in front, and in fact, if you wanted to get rid of the fraction, you could distribute the 3 through the first factor.